Exciting session here, and we have three invited speakers followed by three contributed student participants. So we will start with Dr. Shibendu Som, who is a group leader and principal computational scientist at Argonne National Lab, and he works on the area of CFD, and his title of presentation is High Performance Computing, Accelerating Fuel Engine Co-Optimization. So I welcome him.
Thank you. Thank you, Mr. Chairman, for the kind introduction. It's really a pleasure to be here. I'd like to thank Professor Basu and Professor Avinash Agarwal. They're here, but really like to thank them for inviting me to give this talk. It's really a pleasure to be here. Alright, so I'm going to change gears a little bit. You've been hearing a lot of experimental talks for the last couple of days. There have been a couple of CFD talks, but my focus is going to be more on high performance computing and how it can help accelerate engine design. So if you heard the keynote from Dr. Gautam Kalgatti yesterday, there was a lot of discussion that fuels and engines need to evolve together. You cannot just keep working on fuels or just keep working on engines. You need to work on it together. So I'm going to talk about this big Department of Energy program in the US that aims at doing that. So before I start, I'd like to acknowledge my sponsors, US Department of Energy. They have been funding this work. A lot of computational core hours that we have been getting at Argonne. Recently we got an allocation of 60 million core hours to do some of these calculations at the supercomputer. I'd like to thank my team. They essentially do the work. I'm the lucky person who gets to travel and present their work. And the people highlighted in bold are essentially the people who have contributed to this specific talk. I'd also like to mention that Kaushik Shah was part of my group. He recently joined Bennett University. He's there in the audience. I have to leave right after lunch today, so if there are questions about my work and in general about the work in my group, Kaushik will be around and I'm sure he'll be happy to take all the hard questions. A lot of the work that we do is with convergent science, so I'd like to acknowledge them as well. I'm not sure if many of you know about Argonne. Looking at the audience, probably most of you do, but I just put out a mandatory slide talking about Argonne. So it's located about 25 miles from Chicago. It's a beautiful campus. Of course, now it doesn't look like that. It's all white now. It snowed a couple of days back. But typically, in summer, fall, it's a very nice place. Looks like that. That's a bird's eye view. We are not government employees. We are essentially part of University of Chicago Argonne LLC, so we are essentially private employees. Our mission is basic science, environmental management, advanced energy technologies. On a good day, we have about 3,000 scientists, 3,000 employees, 1,000 of them are probably scientists having PhD degrees. We do take a lot of summer interns. A lot of our work is actually done by postdocs, and information about internship opportunities, job opportunities for postdocs are typically listed at Argonne website. So going on, I'm going to talk about, my presentation is essentially in two parts. So since this is a CFD talk, I'll talk a little bit about developments. I'm not going to show equations for the sake of time. But I'm going to introduce two different concepts. One is capacity computing, one is capability computing. Then we'll talk about where HPC is going, where is high performance computing going, looking at clusters, current supercomputers, next generation supercomputers. Then we'll talk a little bit about how to scale these simulations on supercomputers. It's not a trivial job, it's a lot of computer science is involved. So we'll take a few minutes to talk about some of these computer science issues, specifically load balancing. That's a key issue for high performance computing. And then we'll go to the meat of the talk that's more on the application side. I'll introduce this Co-Optima program. Basically, it's co-optimizations of engines and fuels together. We'll talk about two issues. The first phase of this Co-Optima program was focused on SI engines. And for SI engines, there are two critical issues. One is cyclic variability. It really inhibits efficiency. And the other one is norm. So our goal was to develop simulation strategies to capture cyclic variability, understand cyclic variability, predict cyclic variability, and then develop a model to capture now. And then, since there are some students in the audience, I'll have some take-home messages for you guys. So this is the 21st century. Typically, engines have been designed like that. We don't want to design engines like that anymore. No offense to anyone here in the audience. But we have supercomputers, and supercomputers are good for many things. Supercomputers are great for multi-objective optimization. Supercomputers are really good for sensitivity analysis, uncertainty modification. But if you want to use a computer to design your engine or fuel, you need to ensure two things. The first thing is your simulations need to be high fidelity across the design space. Okay? So your simulations need to be reliable. Second, your simulations need to be high throughput. So if your design space is big enough, you need to have high throughput so that you can go through all the simulations in a reasonable time. If experiments are faster than simulations, no one is going to use simulations. So I'm going to introduce two concepts. One is capability computing, the other one is capacity computing. So capability computing is on the left, and what this means is this is essentially complementing experimental work. So in cases where it's difficult to do experiments, for example, looking at the flow inside the fuel injector, where time scales and then are really small, it's very difficult to do experiments. So this is where we do high fidelity simulations, run simulations with 1 to 2 micron mesh sizes with LES. And we try to run these simulations on thousands of processors. These simulations take anywhere between 3 weeks to a couple of months. Kaushik has done a bunch of simulations like this. And these simulations really complement experimental data. So we call this capability computing. The other approach is capacity computing, where we do what industry does. So industry typically runs 50 to 100 cases to optimize their engine design, to optimize their piston bowl. But we believe that if you're running only 50 to 100 cases, you're definitely missing some optimums. So we don't want to miss any optimums. So we want to do capacity computing, where we are able to run thousands and thousands of cases, all within 2 to 3 weeks. Okay? So if thousands of cases have to be run, they may take 3 to 4 months in the industry. We are able to do this in 2 to 3 weeks with our computing resources and some of the tools that we have developed for job management. So key message, capability computing and capacity computing. Okay. Now, a little bit of history here. So this was the first Cray supercomputer that was built. Maybe some of you remember this, but the size of this is actually the size of this room. And the computing power of this now resides in an iPad too. Now, the supercomputer that we have at Argonne is a 10 petaflop supercomputer. It's called NIDA, and the computing power of this is actually 60 million iPads. Okay? And Apple hasn't made 60 million iPads yet. So that's the computing power we have. Can we use it to do something useful? Is the question. So in 2013, 2015, we were spending a lot of time in scaling our codes on clusters. Now we are able to run our cases on supercomputers very seamlessly. In 2021, we are proud to say that Argonne is going to get the first exascale machine, first exascale machine in the world. Exascale machine means that we are able to do 10 power 18 calculations per second. Okay, that's the meaning of exascale. And it's going to be called Aurora, and it's going to be the fastest supercomputer for 3 months. We are in race with China. Within 3 months, China is going to catch up. So we are proud to say that we'll have the first supercomputer. But the key thing is we already know the architecture of the next generation supercomputer. We have a rack of this supercomputer already at Argonne. So we have actually ported our engine simulations on this rack, and we are already testing our simulations on how they would scale on the next generation architecture, so that when the next generation production machine is available, Aurora is available, we are able to run our simulations seamlessly. So that's the goal. Now, how do we do this? A little bit of refresher course on scalability here. So I titled this slide as computational bottlenecks for high performance computing. What I'm showing here is on y-axis speed up, on x-axis the number of processors. Okay? So typically if you increase the number of processors, your runtime should decrease. If you double the number of processors, your runtime should become half. Okay? So that's the 45-degree line, that's the ideal speed up line. It never happens like that. In reality, the actual speed up is what you see in that solid line. And there are many reasons for this. The first reason could be communication, could be load balance, could be input-output, I/O, could be memory, and all these things are very, very tricky to understand and to optimize for. The other thing is, if you look at a cluster versus a supercomputer, supercomputer is really less forgiving. It has lower RAM, it has specific nodes to do I/O, it has slower cores. So you really need to optimize your code to run on a supercomputer. Otherwise, you are basically throwing away core hours on a supercomputer. Okay. So at Argonne, we have the privilege, we have computational scientists at the lab who actually helped us with a lot of these optimizations. Okay. So being mechanical engineers, some of these things are difficult for us. But being at Argonne, we were able to get some help from the computational scientists. The key thing with the supercomputer is you need massive parallelism. So typically on a supercomputer, academic codes are being run. But more recently, we are also able to run commercial codes on the supercomputer. So the first thing that we did in order to run cases on a supercomputer was implemented this load balancing algorithm called METIS. So what METIS does is, this is a simulation of a CAT single cylinder engine run on 256 cores. So the x-axis is number of cores, the y-axis is cell count. The blue symbols are results without METIS, and you can see that if we do not use METIS, there are several cores that have 0 cells. Okay? And consequently, there are several cores that have more than 12,000 cells. So the cores that have more than 12,000 cells essentially run out of memory, and what we observe is that this simulation doesn't go beyond top dead center. So then we implemented METIS in collaboration with Convergent Science, and these are the red symbols now. And you can clearly see that the load balance has improved a lot. There are no cores with 0 cells. There are no cores with more than 6,000 cells. So there is still a scatter which is expected, but we are able to actually run these simulations beyond top dead center. Okay? So improved load balancing was the first step towards improved scalability. The other thing that we learned was that we looked at the literature on load balancing combustion simulations. So if you look at this piston engine simulation here, if we use METIS and if we load balance this case, say we have 1,000 cells here and 1,000 cells here. So we have 1,000 cells on processor P1, 1,000 cells on processor P2. According to METIS, that's a good load balance, but in reality it's not, because even though they have only 1,000 process cells, the computational load is different because the chemistry is very different between P1 and P2. So we actually came up with a way to load balance based on the actual load from the previous time step. Okay. So this is something again that we implemented in the Converge code. We wrote a couple of papers on this because we were surprised to see that there are a lot of people doing combustion modeling, but people haven't done this. So we wrote a couple of papers about this that we published. So quite happy with this. So this was the second step towards improved scalability. And the other thing is communication. So communication is a bottleneck. It's essentially associated with exchanging cell information with the neighboring processors. And we have to do this during every mesh balancing cycle. And the original algorithm that we had, this was very sequential. Every rank or every processor was receiving the data it needs from its neighboring cells in a sequential fashion. So if you look at a typical scalability curve, on the x-axis there you are seeing number of cores. If you see the red lines, you see that as we increase the number of cores, the time for communication was increasing. That's not acceptable at all. Okay, so we implemented some advanced MPI all-to-all commands. Again, this is computational scientists at Argonne helping us out, and this actually helps us. We are able to exchange data between all ranks simultaneously, data between all processors simultaneously, and this is really low-hanging fruit, but we are able to get 1000x speed up. So then we did similar things with I/O and a bunch of other things that really helped us scale output. So now that our code scales fairly well on the supercomputer, we also wanted to focus on capacity computing. Like I said earlier, say we want to run thousands of cases. Even if you have an army of people working for you, you don't want to do that manually. It's a very tiresome job to track cases. Okay? So we developed this, at Argonne, this flow manager was developed, workflow manager. This is a hot topic in the supercomputing world. It's called Swift. It automates the job branching scripts, it automates the restarts, it accounts for error handling. It also does some amount of pre and post processing. Okay? So now if you want to run 12,000 cases, each on 64 processors, we can use the 768,000 processors that are available on Mira to do the simulation. And in fact, we have done this gasoline compression ignition concept that was introduced by Gautam yesterday for Dr. Steve Ciatti, who has been a big proponent of gasoline compression ignition at Argonne. We did some simulations for him. We actually ran 2,000 engine simulations in 4 days, typically in industry that would have taken months. Okay. So now that we are ready, our code is ready to do both capacity and capability computing. I'm going to show you some applications. I'm going to first introduce this program called Co-Optima. As the name suggests, it's co-optimizations of fuels and engines. Like Gautam said yesterday, it's true in the US also. Typically, the fuel companies don't like to talk to the engine companies, and engine companies do not like to talk to the fuel companies. So that's where a national lab comes in. That's where universities come in. So this is a program with 9 national labs, about 15 universities, and the goal is to essentially generate a database. Okay? So engines designed to be run more efficiently on affordable, scalable, and sustainable fuels. Fuels designed to work in high efficiency, low emission engines. And then there is also a strategy to bring this to marketplace. Doing research is fine, but essentially most of the research falls in the valley of death. Okay? So we have a strategy to bring this to marketplace also. And then there are more detailed goals, reduce petroleum consumption in US by billions of barrels, etc., etc. There's a lot of information about this program, so I'm not going to talk about it. My slides can be made available also if you want to learn more about the program. But essentially, I co-lead this team. It's called Toolkit Development, and our goal is essentially to do high fidelity 3D simulations, because we believe that the ultimate co-optimization, if that ever happens, is going to happen in a computer. It's very difficult to do the co-optimization in an engine. So in order to do this co-optimization, we have been developing several tools. We have been collaborating with different national labs, different universities. So we do the 3D engine CFD. People around us supply us fast chemistry solvers, extremely reduced reaction mechanisms, for example, properties for these weird fuels, oxygenated fuels that we are looking at, etc. So we do the 3D simulations, we pass on information to do 1D simulations, and then at Argonne we also do vehicle level simulations. And that's the whole idea, that the co-optimization is actually going to happen in simulations. So like I said earlier, the first thrust of this program was light-duty SI engines. And for modern SI engines, there are essentially 2 key challenges. There may be more, but we are essentially focused on, can we understand this phenomenon of cyclic variability? Can we predict it using simulations? Typically, modern SI engines are run on the ragged edge of stability. So if you change your spark timing a little bit, you can go from a stable operation to an extremely unstable operation, very easy now, for example. So we want to understand and predict cyclic variability. In order to develop models to do this, we are looking at this optical engine from Sandia. The data comes from Dr. Magnus Soberg at Sandia, and it's a neat setup. It's a modern SI engine, updated from a GM setup. And the laser plane there is unique because it goes through in between the spark gap. So we are able to get PIV data and combustion data at that laser plane. In order to do the simulations, we actually developed this new approach. It's called Parallel Perturbation Method. This was developed in collaboration with GM R&D. We have a paper that's cited there. In general, when you want to study cyclic variability in experiments or simulations, typically experiments run for 1,000 cycles, and then they look at the COVs, etc., the statistics from 1,000 cycles. Simulations, each cycle takes anywhere between 3 to 4 days. So if you want to run 1,000 cycles, you can easily do the math. It may take you 10 years to get 1,000 cycles, or 10 months, sorry, not years. So that's not acceptable. You can run 1,000 engine cycles in 3 minutes, whereas if it takes 10 months to run 1,000 engine cycles in simulations, no one is going to use simulations for anything, right? So we came up with this approach. It's called Parallel Perturbation Method, where we run a couple of LES cycles, then based on the length and time scales of the engine, based on the clearance height, based on the engine RPM, we add some perturbations. Okay? And then instead of running through this cycle for 1,000 cycles, we break it up into hundreds and thousands of parallel cycles, and then we run these parallel cycles for a couple of cycles and take the statistics at the end of this. And we have confirmed that the statistics that we get by running this parallel approach compared to a sequential approach is the same, and that's what is discussed in that paper there. So now that we have this approach, let's look at some results. First, we are looking at some motoring results. Typically, motoring data is easier to match. So I don't want to go into much details here, but these are LES calculations. Each cycle takes about 2 days here. And the data here is unique, so we are able to visualize the cut plane going through the spark plug gap, and you can, in general, see that the velocity contours look quite similar. The pressure is well matched as well. So then moving on to combustion, so I have one more slide on this engine. So this is a GDI engine. So we have some data for this VCO GDI injector, and these are constant volume experiments that were done at Sandia again. And what we did here was we had experimental data for liquid penetration, vapor penetration, and spreading angle. So those are the black lines that you see on the right. What we did was we ran LES simulations. We actually ran 50 realizations. Each realization was perturbed in a certain way so that we get some uncertainty from the simulations. Each simulation takes about 10 hours and 32 processors. So the unique thing about this is, if you look at an experimental data, typically experimentalists have error bars. These experiments don't have error bars, but these simulations do. So that's the goal from my research group, that we want to do uncertainty on all our simulations and provide error bars from simulations as well. So you can see some of these error bars here. So in general, the match is reasonable. The spreading angle could be matched better, but like Kaushik would say, in general, spray cone angle, spray spreading is difficult to match. So in general, we are quite happy with the match. So then we move on to the combustion results. And for combustion results, first we compare the consecutive cycle results on the left with the parallel cycle results on the right. The 50 cycles, so experiments are blue, simulations are red. These 50 cycles took about 3 months to run. These 98 parallel simulation cycles were run in a couple of weeks. So that's where you see the advantage. And in terms of results, experiments give COV of Pmax of 7.64. Simulations tend to over-predict. But the key thing is the trend. So this is just one condition. We have looked at a couple of other conditions, and the simulations, the parallel approach gets the trends right. So if there is a lower COV, the parallel approach gets the lower COV right. So quantitatively we may be missing, but we are getting the trends right, and that's what is typically simulations are being used for, to get the trends. So moving on, I have this movie, hopefully it plays. Yes. So on the left, we are looking at a cycle number 4. On the right, we are looking at cycle number 5. So left was a high cycle, right was a low cycle. Yes, and you can clearly see that for the low cycle, okay, I'll just say, for the low cycle, the flame actually looks like a potato. The high cycle, the flame actually looks like a pancake. I don't know why that doesn't play properly. After doing these high fidelity LES calculations, we can dig deeper, do some more data analytics to understand more about the simulations. And this is where machine learning comes into the picture. So one of the goals that we have had is, can we do these cold flow calculations? Now that we have done a lot of these combustion calculations, can we use this information to develop a machine learning model where we can then just do cold flow calculations, and based on velocities and equivalence ratios distribution in the spark plug gap, based on cold flow calculation, could we actually predict if it would be a high cycle or a low cycle? So that's one of the goals that we have that we are exploring. So the last part of my talk is knock modeling. This is another key issue for spark ignition engines. I'm not going to talk about this slide in detail. Gautam talked about it in some detail yesterday. But the goal here is to have a model to predict engine knock. Okay? There has been a lot of work done in this field for the last 20 years. A lot of phenomenological models exist. We want to develop a model that works very well in a 3D CFD fashion. Now, in order to test an engine knock model, we thought we'd use the CFR engine. CFR engine is the actual engine where they measure RON and MON. Okay? So this is probably the ideal engine to test your knock models. So the approach that we have developed is implemented in Converge. This is a hybrid turbulent combustion model where we use a level set G equation approach to track the flame. Okay? And we use flame speed tabulation, and this is where the new model comes in. In general, if you're looking at simple fuel like isooctane and heptane or a PRF mixture, there are correlations for flame speeds, laminar flame speeds for this fuel. But if you're going to look at some fancy fuels, some low octane fuels, or for example, some oxygenated fuels from Co-Optima, there are no correlations available. So we have developed a technique where we actually run ChemKin 1D plane calculations with detailed chemistry and tabulate the flame speeds for different pressures, temperatures, equivalence ratios, dilution ratios, etc. So we tabulate the flame speed that feeds into the G equation. And then we use the multi-zone approach to get the end gas out of emission. We use really small time steps. We usually use very small mesh sizes. In this case, we are actually using a real CFR geometry. There is a lot of work on some made-up CFR geometries, but we actually got the CFR engine at Argon measured, and we have the right dimensions. In terms of mechanism, Livermore has developed a new mechanism for gasoline ethanol surrogate blend that we are using for our simulations. So the goal here was to calculate the critical compression ratio. The black line here is essentially the critical compression ratio. So if the compression ratio is above this, it knocks. If it's below, it doesn't knock. So our simulations were able to capture the green dots essentially are the critical compression ratios predicted from simulations, and we are able to match the experimental results very well. On the bottom, for a fixed compression ratio, we are looking at the PRF effect. So PRF 71, 87, and 98, and you can clearly see that if the PRF number is high, the knock is low, which is what is expected. So with that, just a couple of ending slides. A lot of our collaborators I want to acknowledge. Today we got to speak about some of the work, but we do a lot of work on nozzle flows, two-phase flows, diesel engines, diesel sprays, gasoline sprays, Lagrangian or radiant modeling. We also do a lot of work on uncertainty analysis, compute heat transfer, etc. So we didn't get a chance to talk about it, but in the future, hopefully we can come back and talk about it. And since there are some students in the audience, I wanted to leave you with a couple of messages. So like Gautam said yesterday, we believe this very strongly that there is still significant room to optimize engine combustion systems. But this optimization has to be done together with engines and fuels. A couple of years back, I did a series of talks saying HPC can enable a paradigm shift in engine CFD. Now I believe that HPC can enable a paradigm shift in engine design because we believe our simulations are predictive enough to affect engine design. There are a lot of students. I would strongly encourage you to take courses in parallel compute. That's the future. Okay? For me, my group, we have sort of done this on the job. Same with machine learning. We have sort of learned it on the job, but going forward, we'd like to hire people who already have this background, parallel computing, machine learning, etc. And we also believe that uncertainty quantification is going to become more and more important for both experiments and simulations. So encourage if there are opportunities in math department, computer science department to take these courses, I would strongly encourage that. With that, I've probably eaten into a couple of minutes of Kalyan's time, but I'll be happy to take any questions. Thank you.
So thank you, Dr. So. Do you have questions from audience? Yes?
So excellent talk, Shivendra. Thank you for summarizing all the work that you've done at Argon. Excellent.
Thank you.
So the one question I had was when you talked about using parallel computing to do the cyclic variation simulations. So you mentioned that for the first 35 simulations you ran LES calculations, and this was basically done to get all of the initial conditions right. Because one of the things that I was thinking about was one cycle feeds into the next.
Right.
Right. So how do you ensure that the exact cycle, the end of cycle effects are captured in the next cycle?
So that's an excellent question. We have been asked that question multiple times by using this parallel approach. So the first thing is those experiments were only run for 35 cycles. So that's why the simulations were run for 35 cycles. Our approach is to run 2 cycles and then feed in the perturbations.
Okay.
And once we feed in the perturbations, we run these 35 parallel cycles, and then we look at the statistics, so COV, etc. We are interested in the statistics in the data and how that statistics compares with the experimental data. In this parallel approach, it's almost impossible to stitch together the cycles. So there is no way of knowing that this cycle would happen after this cycle or this cycle. But we believe that if we run enough number of cycles, we can even run 1,000 cycles, for example, but if we run enough number of cycles, we can actually get the highs and lows correctly predicted with this approach. So we cannot predict which cycle comes after which cycle, but we can get the stochastics, the statistics correctly predicted. And that's the goal of the approach. Next question. Yes.
In the knock model, which scheme do you use?
Yeah, so this is a new mechanism that Bill Pitts and his group developed just for co-optima. It's for ethanol PRF blend. It's not published yet.
Okay.
So we had an older model that we tried, it wasn't doing well. Essentially the isooctane chemistry was too slow. So they have now updated the isooctane chemistry, and we are getting some nice results now. Hopefully we'll be able to publish it soon.
Yes.
So regarding GDI, as you mentioned that you are using isooctane as a reference period. So in case of SI, this is a good representative, but I think when we are planning for this spray characterization, then it might not be, because this for the single component fuels and gasoline, it might be different evaluation characteristics.
That's a very good question. So maybe I didn't explain it well. The GDI constant volume experiments were actually done with isooctane. So we used isooctane for validation. Typically when we use gasoline fuel, we tend to use for chemistry at least a PPRF representation. If we have ethanol, then we also use ethanol. But that's an excellent question. In this case, the experimental data was also isooctane. Now, when we look at the engine results, the engine experiments were done initially with isooctane. There have been some gasoline, and there have been some gasoline ethanol blends. So that's why we have these chemistry mechanisms also that complement this, the experiments.
Yeah, please.
I wanted to ask, what is the acceptable limit for the cyclic variation, coefficient of variance? It's in this spark ignition direction.
I'm not an experimentalist, maybe you can say, but I think it's about 3%. Any data that has more COV than 3% is typically thrown out. So
When the engines won't run properly.
yeah, the engine. So I think 3% is probably the limit, is my understanding.
Okay, let's thank Dr. Som with the rest of the faculty. So our next speaker is Dr. Kalyan Kumar Srinivasan. He's a professor at University of Alabama, and he will be talking about strategies to achieve high brake thermal efficiencies in low temperature dual fuel combustion.
Thank you. Thank you, Mr. Chairman. All right. Thank you again, Chairman. And I would like to express my pleasure for having been given this opportunity to talk about some of my research. And I would like to thank Professor Basu and Professor Agarwal, who I believe are not here right now. And also, I would like to place on record one thing. I had the opportunity to judge some of the student posters yesterday, and I wanted to go ahead and say that some of the work that I noticed was excellent. So this was really good work, and I was happy to be part of that whole experience. So without much ado, let me just go ahead and start this discussion. So my talk is titled Strategies to Achieve High Efficiencies in Low Temperature Combustion Dual Fuel Engines. And the key thing here is preliminary observation from single cylinder experiments. I want to emphasize preliminary because no attempt has been made to optimize the combustion here. This was just the first set of experiments that we ran, and I'm just going to go ahead and discuss some of the thermodynamic implications of what we found. So this is a brief outline of the presentation. I'm not going to go over this because I'll be talking more about this. So by way of introduction, I graduated with a PhD in 2006, moved to Mississippi State, built a combustion engines program there. I was there for 11 years, and I just moved to the University of Alabama. I've just been there for 6 months. So I'm actually setting up a single cylinder test cell to complement the existing research facilities there. So this is just a snapshot of everything that goes on at the University of Alabama. We have a strong faculty, about 8 of us that work in the area of combustion and engines. And there's a whole bunch of work that we do from pure combustion, spray studies, and with engines. So I wanted to go ahead and dress up this little cartoon that I drew up to introduce the audience to dual fuel LTC, although I do know most of you probably know what this is. This goes back to some work that I did way back in 2006, but this cartoon is still valid to go ahead and capture what happens in dual fuel low temperature combustion. So you have lean, you induct a lean natural gas air mixture, and then you inject diesel. So the point is go ahead and make use of the inherent difference in ignition characteristics of both of these fuels. Natural gas happens to be on the higher end of the octane scale, meaning that it resists auto ignition, and diesel happens to be on the lower end of the cetane scale, which means it's easy to auto ignite. So with these difference in ignition characteristics, a lot of things can be done in cylinder. So the difference here to achieve low temperature combustion is by advancing your injection timing well before top dead center. So the typical injection timings that we look at are about 300 degrees or 60 degrees before top dead center. So you have a small amount of diesel that is injected, typically about 500 to 700 bar. We noticed that using high injection pressures, as Professor Kalgaki mentioned, is not a good strategy because we have quite a bit of wall wetting, and this leads to other problems. So around 500 bar is what we've used, and it's given us pretty good results. So this disperses the diesel within the combustion chamber. So at the time when the conditions in the cylinder are conducive to ignition, the diesel preferentially auto-ignites compared to natural gas, because natural gas is primarily composed of mostly methane, which resists auto-ignition. So the distributed ignition centers enable fast burn rates, leading to better fuel conversion efficiencies on the one hand. On the other hand, the lean burn of natural gas air mixture practically results in low local temperatures. And because of the lean burn, we don't have PM, and we have very low NOx. And this is how low temperature combustion is typically achieved in dual fuel engines. So this sets the stage for the rest of my talk. So this talk is based on it's an outcome of a detailed experimental program that we did while I was still at Mississippi State. So all of the work that I'm going to talk about comes from a single cylinder engine. So one of the things that we did was we did a complete sweep of the injection timings at which you can inject diesel. We had only one diesel injection, so that we didn't want to go ahead and add the effects of different diesel injections in there. We were not trying to optimize anything. More like we wanted to go ahead and sweep the injection timing space to go ahead and see what were the different regimes of combustion that you can traverse by going from very retarded combustion, start of ignition timings to very advanced start of injection timings for diesel. So what we noticed was in our particular experiments, when we kept the engine load at 5 bar BMEP, the engine was run at 1,500 revolutions per minute, and the inlet pressure was 1.5 bar. And what we noticed at about 50 degrees before top dead center, or 310 CAD, we had very low engine out NOx emissions. On the flip side though, we had pretty high unburned hydrocarbon and carbon monoxide emissions. So you actually have a NOx versus head C trade-off in these low temperature dual fuel engines. So the focus of this talk is basically go ahead and see, okay, now you pretty much achieved your NOx, you've zeroed out your NOx almost. The question is, how can you bring down the unburned hydrocarbon emissions without too much a penalty on the NOx emissions? So this particular experiment focused on fixing the injection timing at 3 ton CAD and then varying the ratio of diesel to methane in the cylinder to go ahead and see what effects this has on the nature of dual fuel combustion and if it can be used as an effective strategy to go ahead and reduce the hydrocarbon emissions. Okay, so those are basically the primary objectives of this study. So the engine that we used was a single-cylinder research engine. It was modeled, so this one is a one-cylinder version of an engine that Hyundai used for its buses in South Korea. Many years ago when I was starting my career at Mississippi State, we found this company in South Korea who was able to build this engine for us. This engine has been my bread and butter mostly for experimental work for the last 11 or 12 years. So it has a common diesel injection system, and we had all kinds of instrumentation on this. The key thing to note is the baseline geometric compression ratio is 17:1, so it's a 4-valve overhead OHV engine. So the first thing that I want to talk about is cylinder pressure and AHRR. So what we did was we fixed the injection timing at 3 ton CAD and we changed the relative percentage of, or we changed the methane energy fraction. So we adjusted the diesel and methane to ensure that the engine load was maintained a constant at 5 bar PMEP always. So that was how we did this suite of experiments. So one thing you can note from this is from the pressure curves, you have pretty high, so with the decreasing methane energy fraction, that is when you go from 90% substitution all the way down to 70% substitution, the peak pressures increase significantly. That's one thing. There are extremely high magnitude of combustion heat release rates, which is evident by the purple curve on the lower left. There's significant low temperature heat release activity when you increase the fraction of diesel compared to that of methane or reduce the amount of methane with respect to diesel. And also the combustion phasing or CA50 is advanced significantly. It is actually well before top 10 center, which is going to be one of the things that I talk about. The second thing is we looked at the bulk temperature and the apparent heat release rates just to go ahead and see if we can look at what's happening here in terms of does this impact the the low temperature heat release, particularly we're looking at the low temperature heat release, and we wanted to see if the impact of this LTHR was captured in the bulk heat release, bulk temperatures, which is evident, you can see that. So with decreasing methane energy fraction, the following are true. The compression temperatures are lowered by about 40 Kelvin. You can see that from the lower black line to the green line there, 660 to maybe 620 or so. And this is particularly from a specific heat effect. Because when you have higher amounts of methane, you have more specific heat, and because of that, the end of compression temperatures would actually be lower. And you're actually seeing that in experiments. Okay? So the second thing is the phasing of the LTHR. So you can see that in the lower left plot, against crank angle, the peak of the low temperature heat release is significantly advanced with the decreasing amount of methane in the cylinder. Okay, and then one important thing to note is at 90% substitution of methane, you have very little, almost near zero low temperature heat release activity, and this has a significant impact on what happens later in terms of engine out emissions and other things, which I will talk about. So we took this one step further, and then we wanted to do one more thing. So what we did was, the typical plots are AHRR versus CAD, or the average cylinder temperature versus the crank angle. So that's common. What we ended up trying to do here was to go ahead and capture one thing we wanted to ascertain. Although there's a lot of literature that tells us that because of the difference in the ignition characteristics of diesel and methane, all of the low temperature activity should come from diesel. So how would you ascertain this from simple experimental data, right? So what we did was we plotted the apparent heat release rate with respect to the bulk cylinder temperatures. And what we noticed is all of the LTHRs that you saw in the previous plot, I'll bring that up for reference again. Okay, right there. Okay, if you see with respect to CAD, there's a lot of shifting of the LTHR peaks with respect to the crank angle. Now, if you try to look at the LTHR peaks with respect to the bulk temperature, they kind of align up. You know, there's a little bit of a difference, but they all align. The other thing that we noticed is the start and end of the low temperature heat release, okay, in terms of temperature, because that's what's important, right? What we noticed is between the LTHR predominantly occurs between 650 and 750 Kelvin, okay, when you change the methane energy fraction. This is indicative of the fact that LTHR is predominantly due to diesel, and there's very little methane involvement here, okay? So this sort of gives us more confidence that, you know, really, if you want to try to model this, you want to build a simple zero-dimensional model for trying to do other kinds of optimization. It's, you know, if you're trying to build a VB-based model or something of that sort, it's important to know this information so that you can actually build your VB. You can select your VB coefficients accordingly so that you can get better predictions with your VB-based models. But the other thing here is high magnitude of LTHR influences HTHR, that is high temperature heat release takeoff. So when you have at 70% methane energy fraction in particular, you have high magnitudes of the low temperature heat release rate. And this also, you know, advances the start of the high temperature heat release. So this has a relationship, right? So what happens here is, because of this, we were able to see about 12 bar per degree maximum pressurized rates, which for a single cylinder engine, we kind of pegged this that we don't want to exceed 10 bar per degree because we'd end up you know, damaging the head. In fact, we actually did in this particular set of experiments. So we had a cracked cylinder head, and we had to go and you know, find a replacement for it. So that was something that we learned. However, the coefficient of variation of INEP is really small. It's about 1.5%. Okay, and this is because of near knocking conditions, and this is extremely repetitive. And the other thing that I failed to mention is the data that we got here. The cylinder pressure data was over 1,000 consecutive cycles. So we have a lot of confidence in the COV that we get, that we estimate. The second thing is the low magnitude of LTHR retards the high temperature heat release rate, which is also evident at 90% methane substitution. You practically don't have any low temperature heat release. So the main heat release is shifted after contact center. Now, the other thing this leads to is, of course, this leads to better phasing of the CA50. So your MPRR is a lot lower, it's about 2.5 bar per degree, but the COV of IMEP was 4%. Because one other thing that I failed to mention here is the overall equivalence ratios that you're looking at for this set of experiments is anywhere between 0.3 to 0.4, really lean, okay? So when this happens, you know, when you change the relative fractions of methane and diesel, you're changing the in-cylinder reactivity, which is basically what happens in RCCI combustion anyway, right? This is exactly what's happening here, okay? So when you decrease the amount of diesel and you increase the amount of methane, and then you distribute the diesel in the cylinder, if your ignition centers are not properly distributed, if you don't have robust ignition, then you're not going to have good combustion either, and that results in high COV IMEP. So this is why we stopped at 90% methane energy substitution. We could have gone to 95. I looked at the data at 95% substitution. It wasn't really good. So I decided not to include it in this presentation. So the next thing is obviously, you know, engine out emissions. What is the impact on engine out emissions from all of this? So with the decreasing methane energy fraction, we're following it again through, the engine out hydrocarbon and carbon monoxide emissions do decrease as we originally hypothesized. We thought that because we have more diesel in there, this is going to enable the burning of methane, and this would result in a decreased engine out HC emission. Then that's irrelevant. If you look at the green curve, the indicated specific HC emissions, the scale is on the left side. At 90% substitution, you have almost 35 grams per kilowatt hour. That's like huge, right? No engine operates at those levels. Even an oxy can't take those levels, right? So you need to be operating at a much lower methane energy fraction, or you have to do other things to ensure that you can bring your hydrocarbons down, which other things that we have tried are definitely multiple injections, which does significantly reduce the engine out hydrocarbons. I'm not going to talk about that here. So you can, at about 70 or 75 percent methane energy fraction, your indicated specific hydrocarbons is about 10 to 15 grams per kilowatt hour. Even that is high, but it's much lower than the original baseline value at 90% methane fraction. The carbon monoxide emissions also decrease with decreasing methane fraction. The trade-off is NOx. You can see the blue curve. As you decrease the amount of methane in the cylinder, your NOx actually exponentially increases. You go from almost 0.3, 0.4 gram per kilowatt hour to 3.5 gram per kilowatt hour. So that's a significant trade-off. So if you're trying to optimize the solid combustion, of course, there are not many levers here. There's no EGR, that's one thing. Okay, there's absolutely no dilution here. And the study was undertaken to try to study the impact of, okay, without all of these things, what happens? This is sort of a baseline. And from here, if you want to go ahead and optimize this combustion, there are several levers that you can use. Multiple injections, EGR, you can play around with controlling the temperature of the EGR, that is uncooled EGR, and things like that, many different things that you can do. So this kind of summarizes the experimental program that we did. And then finally, this is what I really wanted to talk about, combustion and indicated efficiencies. So one of the things that happens is that very high methane energy fractions, you will see that the blue curve on top, that's a combustion efficiency. It's about 78.6, that's really, really low. Okay, typical combustion efficiencies for reference with gasoline and diesel engines, clean diesel and SI gasoline engines, are well above 98%. Okay, so the effort is, so one of the other things was to try to say, okay, can you increase the combustion efficiency? Or by changing the relative fractions of diesel and methane in the cylinder, will the combustion efficiency increase? And we knew the answer to this when we started doing the experiment. Yes, you will be able to increase the combustion efficiency, but the big question there was, does this increase in combustion efficiency translate to an increase in indicated efficiency? So that's where I have, the reality is the orange curve. And the expectation was that you probably have a similar behavior in the indicated efficiency, but it's not like that. And the answer to that is in the lower half of the slide. This is CA50. The important variable here is CA50, as Dr. Kagaki mentioned in his presentation. Phasing the CA50 is critical. You need to ensure that it's optimally phased. Now, because we didn't use other levers in this experiment, for example, no EGR, and we didn't have multiple injection timings, or there's no other way to ensure this CA50 being a constant. We allowed it to vary just to see, okay, what's the worst that can happen, right? And then you see obviously that there's a linear trend in CA50, which means so the CA50 is progressively advanced as you decrease the methane energy fraction, and it gets advanced so much that the centroid of your combustion occurs even during the compression stroke, and that's a no-no. I mean, simply from very basic piston energy dynamics, you don't want your start of combustion or your centroid of your combustion to happen even when you're compressing the contents of the cylinder. That's a no-no, right? Because it's against all principles of trying to extract useful work, right? That is what led to the decrease in the indicated efficiencies. So the other thing is, advanced CA50. So what can this do? I haven't presented this data here. The thing that it does is it increases your exhaust temperatures. So where does all this go? So the increase in combustion efficiency helps in lowering your hydrocarbons. It helps in lowering your carbon monoxide emissions, but it doesn't get translated to useful work. So what happens to it? We went and looked at indirect evidence of this because we didn't try to measure we didn't have heat flux meters in there to know if there was any significant change in the heat transfer. We could have gone ahead and calculated using the Boschny correlation, but the indirect quick rule of thumb evidence is go and look at your exhaust temperatures. At 70 degree or 70 methane energy fraction, our exhaust temperatures were significantly higher than at 90. I don't have the data here, but I can confirm that to you. I have the data with me. If you're interested, I can discuss more about that later. All right. So we looked at all of this, and then I said, okay, what are the thermodynamic implications? If you really want to achieve those high efficiencies, what you need to be doing. So I went back to real basics, things that all we know, everything that we know about. So, I have a combustor there, and it has fuel and air coming in at P0 and T0, which are basically the restricted dead states. And then I allow the products also to go down to restricted dead state. And I simply write out for a steady rate process. If you write out the first law and the second law, that's evident. You just have the difference in enthalpy. It's going to be equal to the change in heat transfer minus work transfer. And the second law is also pretty straightforward. You have the entropy change equals the entropy transfer plus the entropy generation, right? So you can eliminate the heat transfer out of this equation, and you can get this nice equation for the W dot from this, right? And this, if you go back to thermodynamic circles, this is what is known as the Guy-Stradola theorem, right? What you end up with here is that T0 times T0 times S dot gen. That particular term in there is that's because of all the irreversibilities in combustion, right? So if you want to find the maximum work that you can achieve from a system of this sort, you allow that S dot gen to become 0, and that's your maximum work. It turns out, if you assume that your fuel, air, and products are all ideal gases, this W dot max is equal to the chemical potential of the fuel, or what we know as the chemical exergy of the fuel, right? So this is what we know. So then, if you add one constraint to this system, if you disallow heat transfer, you make this combustor adiabatic, okay? Then what happens? What happens is that even for such a condition, about 25% of the fuel chemical exergy is destroyed. So what I want to say is, no matter what you do, I don't care what kind of combustion you do. I mean, it can be the best type of combustion that you invented. If you're burning fuel, a hydrocarbon fuel, it is an irreversible process. So what you have to work with is only 75% of the chemical exergy, right? So you want to try to maximize whatever you can get from that, right? So for an actual process, this is what it all boils down to. So what I ended up doing is that W dot, you can actually write it in terms of the combustion efficiency, the indicated efficiency, the gross indicated efficiency, the gas exchange efficiency, and the mechanical efficiency. Because that's the work that you measure at the shaft, okay? So you put all of this together, and then you get this entropy generation in this nice form, chemical exergy minus all of this stuff. So the goal of an engineer, is to try to minimize this entropy generation from combustion, right? So how can you do this? What are the different things you can play with? What are the different levers that you have? See, one thing that we're constrained with is the piston cylinder mechanism is a crank and slider mechanism. So with all that constraints, some desirable characteristics of combustion process to achieve high thermal efficiencies are probably, ensuring high combustion efficiencies, which we already have with current SI and clean diesel combustion engines. For low temperature combustion engines, we're not there yet. So we need to ensure that you meet or achieve similar levels of combustion efficiency. That's one thing. The second thing is reducing friction, which is already being done by changing the different material characteristics and so on and so forth. I'm not an expert in that. I'm not going to talk much about it. The third thing is reducing pumping losses. This we can do. Okay. Minimize exhaust losses. This is possible with low temperature combustion, and also minimize heat transfer. This is also possible with short combustion durations, which means we want to favor rapid combustion. You don't want too long combustion durations. You want to try to keep the combustion durations as short as possible, because if that happens, you don't get enough time for heat transfer from the combustion to the walls, right? All of that can be converted to useful work. Okay. Then you operate at high peak pressures with combustion phasing optimized to occur after TDC to ensure that you have high gross indicated efficiency. To do all of this, you can get pretty high thermal efficiencies. So just to conclude, decreasing methane energy fraction reduces engine out HC with a significant engine out max penalty. And then one thing I want to talk about is despite the advanced phasing of the low temperature heat release with decreasing methane energy fraction, the low temperature heat release activity is between 650 and 750 Kelvin, which is likely only due to diesel. And we're ongoing experiments right now where we're trying to look at are to try to keep the CA50 a constant and allow changes of all other variables to see if we can actually go and get much higher thermal efficiencies. Final thoughts. The focus in the future, I think I'm going to go ahead and attest to what Professor Kulgatki said in his talk. The IC engine is going to continue to be a force to reckon with. What we'll be focusing on, as far as the engine is concerned, is getting to high peak firing pressures, designing more bulky cylinders to ensure that we can take this sort of repetitive load. And then we'll probably have more waste heat recovery, downstream waste heat recovery. And long term and beyond, 2050 and beyond, we'll integrate efforts to larger electrification, allowing all the V2X, V2I, and the connectivity. So the reports of the death of the IC engine are vastly exaggerated. Okay, so this is what I believe, and we are gonna have jobs. Okay, so and I want to acknowledge all of my students who toiled in the lab getting this data. 90% of the time spent fixing the single cylinder test bed, and 10% of the time getting the data. That's when they're not allowed to take bathroom breaks. Okay, they're going to sit there, get the data, then go. That's how we get a PhD, right? So, and particularly I want to thank my student Prabhat Jha, who actually is responsible for all of the view plans. Thank you so much again, and I'm open to questions.
Thank you very much, Professor Kalyan, for an interesting talk. We have questions here.
Well, I was thinking, are you proposing to sort of experiment with different injection designs?
Yes.
The way you look, I mean, I was thinking if you don't have a diesel droplet somewhere in the corner,
No.
that fuel might not unite in the way you run it.
Yes, it's not optimized. So we are looking at low. We did. So one of the things that we're looking at is when we built the new single cylinder experimental test bed is to get different injectors with different umbrella angles. This we know from work from Lund that actually helps a lot in this sort of combustion, partially premix combustion. Yes.
Any other question? No.
Okay. Thank you all, and definitely go home and hug your engine. Okay. You do that.
That is great for you of appreciation. Very good.
Oh, thank you.
So our next speaker is Professor Soni. He is director of NIT Uttarakhand. He had been professor at MNIT Jaipur for a long time. His talk is about emission reduction techniques in automobiles.
This board here. Which is here? It's here. Good morning to all. The topic is emission reduction techniques in automobiles. This is not a very deep study, but it is work done by one of my students, Mr. Pradeep Kumar, for his research degree. Other Professor Dilip Sharma, who is my colleague, we have been doing it. Main focus of this is that we have plenty of engines which are older one, giving lot of emissions, and the greenhouse gas emission from automotive sector is about 1/3 of total. Road transport gives about 75% of these greenhouse emissions. Focus is needed on diesel engines because there's more soot and NOx from them. New engines have to satisfy the BH4, now it's BH6 coming up. But what about the old engines? We are having many engines which are badly maintained and contribute about 60% of the total pollutants from the transport vehicles. Some of the emission reduction techniques can be the engine enhancement, like we can go for changes in fuel injection system, we can go for changes in cylinder design. The alternative fuels can also be used. The vehicular weight is also a major contributor to the emissions from the engine. And the last one is we can go for pre and after treatment of emission reduction techniques like EPF, EGR, DOC, SCR, etc. The work done is on DPF and EGR. A diesel particulate filter is to minimize PM and exhaust gas is minimized in NOx. It is found to be most appropriate in this study. An engine which was older one, it is Mahindra and Mahindra engine, Bharat one. It was 4-cylinder water-cooled direct injection CI engine. EGR optimization was maintained and DPF regeneration was tested by two methods. It's online by using ECU, then off-board also, which was done in the lab itself. Effect of vehicle weight on emission was also studied. This is the experimental setup. I will show it here. We have got an engine, Mahindra Jeep engine. It is Euro 1 water-cooled direct injection CI engine. This muffler and DPF was placed just after the muffler. We had a dynamometer as a current one. Everything was done in the laboratory. We used ECU also. Two methods were there for regeneration of the DPF. One is with ECU, other was off-board. This is the setup for DPF ECU, and the engine specifications are given like this. It is 4-cylinder direct injection Mahindra and Mahindra engine, very old, purchased about 10 years ago, which is used nowadays generally in our old cars, which are Jeeps, and also in very old Mahindra vehicles. The DPF used was tailor-made by an ex-employee of Maruti Suzuki, Dr. Khatri. He is PhD from IIT Delhi. He has got his own industry and he has supplied it for us as per our requirement. We put some strainer before the DPF so that laser source will not come to the DPF. This gives how the strainer in the DPF goes. This is before and after off-board regeneration. Before off-board regeneration it was black one, and after on-board regeneration it was white. This is the setup for EGR. EGR was used to reduce NOx and DPF was used to reduce the smoke. We had the same engine. This is the EGR valve. We had some ECU for EGR and it was done depending upon the requirement of the engine output. This is another setup we used for displaying what is happening with this. The dynamometer was calibrated, gas analyzers and smoke meters were also calibrated. The base case readings were taken for emissions with the load of 0, 25, 50, 75 and 90 Newton meter, and 5 states were there for running the engine. DPF was active to set up, and then other things were taken care of. The off-board regeneration was taken by disassembling the DPF from the setup. It was put in an electric resistance furnace. The temperature maintained was 650 degrees Celsius, It was kept for 10 hours, so that whole of the carbon particles will get converted to CO2. Just remember, without any carbon. The readings for all torques and RPMs with active regeneration of DPF automated using diesel mist spray on the DPF with the help of DPF ECU. Two methods are there. One is off board, other is as per ECU. In case of ECU, I'll just say this is here. Yes. We have ECU, DPF ECU, and there is diesel spray. This diesel spray comes because of the feedback from the ECU, and this spray is made in the DPF so that it will burn because of the higher temperature of exhaust gases, and whole of the particulate matters will going out from the engine. First of all, it was done with DPF, then it was done with EGR. Both are giving different results. Studies were made on how the weight of the vehicle plays a role in reducing the exhaust emission. About 10% reduction in vehicle weight reduces 5 to 8% of fuel consumption, and hence there is reduction in CO2 emission. It is about 9 grams of CO2 per kilometer when you reduce the weight of vehicle by 100 kilograms. It can be 34% reduction in weight achieved by using aluminum alloy as the constituent part of the vehicle. European cars contain an average of 132 kilograms of aluminum components. This has been taken a literature review. Industry is working on how to improve the aluminum alloy for facing the force which is coming on the engine. They can change the material of the engine, they can change the design, size, and footprint can be changed. All about it. 5 to 10% emission reduction for every 10% reduction in vehicle weight shall be there, keeping other parameters same, mainly due to fuel economy. No straight relationship was found by us to establish the vehicle weight and the emissions coming out from the engine. The result of this is we could get 79 to 99% of smoke reduction by using the DPF. This was more after off-board regeneration compared to that after active regeneration. Active regeneration is with ECU, and the off-board regeneration was taking out, disassembling the DPF and putting it into electric furnace. DPF with off-board regeneration did not have any significant impact on engine performance, whereas with active regeneration there was a drop in engine power output. We have literally measured, and just giving the graphs to you. Important to have a feasible and economically viable periodical DPF reduction mechanism for reducing the exhaust, soot and NOx from the engine which are existing in the country. It was increased with DPF, this NOx, but it was reduced when EGR was used, likely because of the lower temperature due to EGR. O2% in exhaust decreased substantially with DPF at all loads due to oxidation of soot embedded in DPF to form CO or CO2. These are some of the graphs of the results. You can see the blue curve gives smoke without DPF. The brown curve, the greenish one, gives smoke with active regeneration, and the red gives smoke with off-board regeneration of the DPF. It is with different RPMs of the engine, the torque is increasing as well as the smoke also. This is normal trend. But if you see the use of DPF, there is very little, almost nil variation in smoke coming out of the exhaust of the engine. These are the practical results data. This is comparison between the off-board regeneration and with active regeneration. Just see, the smoke with off-board regeneration is less as compared to that with active regeneration. Actually speaking, when we go for active regeneration, after certain time of the engine run, we have to open the DPF, go for off-board cleaning, and then again reassemble. So that is taken care of, and that's why we see that there is more smoke with active regeneration than with off-board regeneration. This is about the NOx. NOx increased with DPF, but it is not as much as it was without DPF. It is very less without DPF. Might be because of back pressure, there is an increase in temperature and it is causing NOx to be formed more than without DPF. Oxygen is reducing with torque and with DPF. It is more without DPF and less with DPF. BSFC, brake specific fuel consumption, we can see it's almost equal, but there is an increase in BSFC without DPF and it is reducing with DPF. Difference between active regeneration and off-board regeneration is very less, but it is measured that it is more without DPF when RPM is less, but it is more with DPF when RPM is increased. Similar is condition with the efficiency of the engine. Brake thermal efficiency increases with DPF when the RPM is less, it reduces with DPF when RPM is more. Then we shifted this to an exhaust gas recirculation system. It was an electronic control unit which could change the EGR depending upon the engine temperature. So it was taken at higher loads and different lift of the EGR valves were taken care of. I will give in conclusions. Higher the load, higher exhaust pressure and higher EGR percentage and more fuel penalty. But what we got is the reduction in intake oxygen concentration, decreased flame temperature in the cylinder by increasing the specific heat capacity of the intake charge. This is because of the higher temperature. These are the results with EGR. When there is no EGR, the NOx was very high. When EGR was used, NOx was reduced. At every step you can see A, B, C and D. These are the RPMs. With increase in RPM, no effect on the trends of the curve. With reduction in RPM, there is no effect on the trends of the curves. Curve trends are same, but there is a rise in NOx when EGR was not used. This is about smoke. Unfortunately, it is not affecting. With use of EGR, smoke was more. Without EGR, it was less. Might be because of lesser temperature complete burning was not taking place, and hence we had more smoke. These are the curves for PSFC and for with EGR and without EGR. These graphs are showing the thermal efficiency of the engine. These are the conclusions which can be drawn. The smoke was reduced with use of DPF in Euro 1 engines. DPF adversely affected NOx emission due to back pressure and resultant fuel penalty, increasing combustion temperature. This is one of the reasons which I can think, because of higher the temperature, more NOx are formed. Addition of DPF had adverse impact on BSFC and BT because of the back pressure. Due to soot accumulation, there is problem in the engine performance. The two regenerations, onboard regeneration and ECU regenerations, we have measured a difference. The onboard regeneration was better than the ECU regeneration because it was done after certain time regularly, and hence we could get better performance of onboard regeneration. This is already done. The NOx was reduced because of EGR. The optimum EGR values varied from 22% to 58% at different torques and engine speeds for the setup used. This was an automatic ECU which was controlling the variation of EGR depending upon the temperature in the engine. Though no straight relationship could be established, but it is seen that the 10% reduction in engine weight, the emission reduces to the extent of 5 to 10%. Hence, it is better to say that emissions per unit power generation certainly gets reduced due to the tune of 5 to 10% for every 10% reduction in vehicle weight. These are the references we have taken, and I thank you all. I think I have finished early.
Thank you. So, do you have questions? Yeah.
Yes, sir.
Thanks for the talk. Just a comment, in fact, we have done I suppose this is to highlight the emissions from the old vehicle, which
Yes.
is a big issue.
Yes.
We have done a retrofitment pilot study with USCP and WRI and Johnson Matthey Pudding. And we found that, to be very frank, the Euro 1 engines were not really suitable even for the DOC. The soot load was so bad that DOC with open channel got clogged within no time. And then we tried everything, including the aerodynamics, cleaning, passive regeneration, active regeneration. There were two things. One is the soot load was, PM load was very high, and the temperature was not good because we attempted on city buses. So I think DPF will be a very difficult option for retrofitment, but we can think of, even we tried PF, a partial flow filter, so even that was giving. Another thing we found that vehicle maintenance was a big issue, although we took care quite well. So I think we need to look for other options, but then Euro 2 and Euro 3 could be, or even Euro 4 could be good candidates for retrofitment.
Agreed.
But there are many issues like passive and active regeneration, as you pointed out.
The purpose of this study is to use this for older vehicles. Only purpose is this. Because we have plenty of vehicles and the owners don't want to replace. They want to use the same vehicles. And that can be done with these techniques. If you go for both the things, we can put certain other meshes before the smoke goes to this DPF. It will withhold the higher volume or weight soot particles before it enters this. It can be cleaned with regular intervals. Maintenance is very bad in India. We don't want to go even for the preventive maintenance. How can we go for the breakdown maintenance? The vehicle manufacturers, they give certain times. At this period, you have to service the vehicle, you don't do. Same thing is happening with the cars and buses in Delhi. You might have seen so many CNG buses are getting fired because the unit which is retrofit which is applied in the buses is not maintained. That's the poor thing we have. Even you can see the trucks which are plying on the roads, they are giving very high amount of black smoke. Might be due to higher load on the vehicle or due to not maintaining the pump and injector regularly. This is the poor thing.
I think Ray has something.
Yes, sir.
Yeah, quick follow-up question, Dr. Soni. Very interesting talk. Now, in the retrofitment option that one thinks about for old vehicles, Euro 1 will obviously, the vehicles will get phased out in the foreseeable next few years.
Yes.
But Euro 2, Euro 3 vehicles, what do you foresee as the opportunities for weight reduction during the retrofitting process? Because obviously whatever we are adding will actually increase weight. Are there compensatory options for weight reduction?
The retrofit which is not very heavy, just see the dimensions of this which we used.
About 5 kg.
See here. The thickness was very, very small. It is ceramic coating. And this is ceramic material which was used, and the weight was not very high. But the only thing is, making this fitted in the vehicle requires certain modifications in the exhaust pipeline. Second thing, every operator of the vehicle will not be ready to do it. Even in catalytic converters we are using in the vehicle today, they are replacing the catalytic converters after it is old with a simple fake device. They put it, that it is seen that it is a converter, catalytic converter, but it is not there. They just waste the time. Any question, please?
Any other question? I had a small query.
Yes, sir.
You use an extra piece of strainer just before the DPF.
Yes.
Did you open it and see how frequently you are getting very big
We
volume?
operated after every 4, 5 or 7 cycles. It was done for 10 hours a day. It was done with different torques. And then we saw it was having some black deposits on the strainer also. So it was cleaned by kerosene or diesel before it was refitted. We had to do it, otherwise it will be clogged and again knocks will be more. And this is done.
Okay, let's thank Dr. Soni.
Thank you, sir.
Small token of appreciation from the society. So now we have some presentations by 3 participatory students. So the topics are kinetic modeling. The first one is kinetic modeling and experimental study. The first one is kinetic modeling and experimental study of small esters, methyl acetate and ethyl acetate. And the speaker is he here? Fazena. Not here? Nobody? Okay, we'll go to the next one, which is from Kayas, Sunguk Lee. He will be presenting on LPG combustion phase control in linked stratified spark ignition engine.
Hi, good morning. This is Sang Lee, who comes from KAIST in South Korea. And this research was conducted with my coworker, Ms. Park, and supervised by Professor Chun-Sik Baek. My title is LPG combustion base control in lean stratified spark ignition combustion engine. My contents are like in here. Let me begin with the background. Just a simple emission regulations. As you know, the emission regulations are keep stricter than before. Representatively, the carbon dioxide is also the regulation for carbon dioxide is also getting stricter than before. So the researchers who are involved in the engine field should improve the engine fuel economy to meet the emission regulation or to satisfy the consumers' the requirements. So in this research, we applied the lean stratified combustion engine that is able to increase the fuel economy. So before to getting my research results, I want to introduce the present research in the field of the lean stratified combustion engine. The left graph shows that the heat release rate graph results within the same injection timing within the different ignition timing, and the right graph shows that the combustion efficiency. So actually the conventional stratified combustion engines combustion base is located a little bit earlier than the ideal location. So to locate this combustion base to ideal location, we should ignite a later time. Then the problem is that, as you can see the right graph, the combustion efficiency is getting worse due to the increased fuel dispersion. As you know, the lean stratified combustion will locate the locally rich mixture in near the spark plug, but if we increase the mixture formation time, then the fuel will be dispersed. So therefore, the participant portion of fuel will be decreased. So this is the problem of the lean stratified combustion engine. So let me begin my research. My objective is we want to locate the combustion base at the theoretically ideal location. As you know, about 0 to 10 practically at the top dead center. So in this research, we apply a throttle valve operation to control the intake air quantity. So it enables to change the in-cylinder pressure and temperature. So let me move on to the experimental setup. So we used a single cylinder research engine. The schematic is here, and the more detailed specification also there. The important properties, we apply the fuel of the normal butane to not just the conventional fuel of gasoline, because it having a higher vaporization pressure, so it is easily vaporized than the conventional fuel of gasoline. So if there is a same mixture formation time, that it will be more mixed. So it having the advantage of some emission characteristics. Let's move on my result. The left graph shows that the heat release rate graph and the in-cylinder pressure twice. As you can see, within the same injection and ignition timing, the combustion base was a little bit retarded than the higher air access ratio. And the right graph shows that the detailed combustion base location and also the combustion base duration. When we decrease the air total quantity, the charge density was decreased. I mean, the in-cylinder pressure was decreased. So within the mixture formation time, the burn duration was increased. So it makes the combustion base retardation. And also within the same ignition timing, the ignition delay was increased. As you can see the right graph. It also made the combustion base retard. So the previous research problem was that the combustion efficiency was lower than the 95%, but all of these research was the combustion efficiency was higher than 95%, except only the lambda of the 1.5 case. And let's move on the mean effective pressure results. The left graph shows that the same mixture formation time within same injection timing, the gross MEP, it shows that but some point is higher than the conventional wide open throttle result. And the right graph shows that actually we conduct many times of injection and ignition timing. We swept about 2 Crank angle degree per 2 Crank angle degree, and without the wide open throttle valve operation, within the decrease the air access ratio, the gross MEP was gradually increased. After a certain value, the value was dropped suddenly. This is due to the too much retarded combustion phase, and also, as I mentioned, the problem is that when we increase the throttle valve operation, as you can see, the bottom of left bar graph, the pumping work was increased. So the net IMP was the result of the net IMP was the decreased all of the results compared with the wide open throttle valve operation. So let me conclude my talk. This research objective was to control the combustion-based location within the lean straight body combustion engine. So we choose to apply the throttle valve operation. The result is here. When we increase the throttle valve operation, then the in-cylinder pressure was dropped. So the time to reach the maximum pressure was increased, and also it makes the combustion phase retardation. So as the previous presenter said, like the portion of the combustion portion was decreased in the process of compression stroke, so the negative work was decreased. So in the end, the gross IMP was increased, but the problem is that the increased pumping works make the total net IMP was in the end decreased. So the PMP increase was the larger than the that of the IMP gross increasing. So the result is here that we are able to control the combustion phase by using a throttle valve, but it is not impossible to improve the fuel economy. So our team planned out to apply the future works. We are going to apply the late intake valve closing and lean straight combustion engine because it can control the intake air quantity or some effective compression ratio without any pumping loss. I mean, not the just variable valve actuation, just with the variable valve duration. So thank you for your kind attention, and if you have any questions, please.
So thank you, Sumuk. And do we have any question for him?
Yeah, yes.
So can you go back to the experimental setup that you
Yeah.
had? Yeah, right there.
Yeah.
So you're using a common rail system?
Yeah, that's right. Yeah.
Why?
Because we inject the fuel with the pressure of 200 bar.
Okay.
Yeah, the previous research was done the effect of the injection pressure, so we conclude that the 200 bar is the ideal pressure for the LPG
So,
injection. Yeah.
but your fuel is normal butane, right? It's not.
Yeah, that's right.
So I wanted to ask you about the fuel composition. You just had 100% butane in there?
Yeah, just actually in the chamber there is a nitrogen and the normal butane, but the injection is 100% of normal butane.
Okay.
And it is really easily vaporized. Yeah. So.
But it's liquid.
Yeah, that's right. Yeah, that's right.
It is liquid, right?
Yeah.
So the thing is, when you actually have the real LPG,
Yeah.
which has different components in there.
That's right. Yeah.
So when you use a common rail, I mean, so have you noticed any issues of vapor formation, you know, right in the lines?
Yeah, they're gonna be happen, yes, but we just want to just check the result of the LPG engine research. So when to apply this real engine is that's gonna be happen that kind of problem. Yeah, that also we should figure out that problem, but we want to check the normal butane just result. Yeah.
Thank you.
Yeah.
Any other question? Yeah.
Which engine you have used for this?
Actually, it is it's just really just a little bit older engine. So we just modified the BMW engine. Actually, it made some about 2000s. I'm not sure, but yeah, just specification is here. Yeah, just yeah.
BMW single.
Yeah, actually the multi-cylinder engine, but we modified to single-cylinder engine.
What is the injection timing that you're using?
Actually, we swept tons of the many times of injection timing, so we find out the ideal injection timing that was 38 before top dead center, the injection timing, because it is a lead straight body engine. Yeah. Yeah.
Okay, let's thank the speaker. So next speaker is Saurabh. Is he here?
Yes.
Yeah. And he'll be talking about evaporation rate analysis of different fuel blends for low temperature combustion engine. So must be loaded already.
So, welcome you all for the presentation. So, I'm Saurabh, I'm from ICNS Lab, IIT Madras. First of all, I want to thank Dr. Kalyan and Dr. Kalgharki for, because I can skip a lot of things in this, in the introduction section. So, this is the outline that I'm going to present. This is a conventional combustion. I'll define why I'm doing this, all these particular things, and why it is important to perform first this evaporation rate analysis. So if this is a conventional combustion, everybody must have seen this DEX model that used to say that higher NOx and PM is common in all these conventional CI engines, and there is a trade-off between NOx and PM. So there is a solution of this is either we can go for in-cylinder emission reduction or tailpipe emission reduction. Tailpipe emission reduction used to after-treatment devices, which is really costly. So we are going for in-cylinder emission reduction. That is low temperature combustion, for which Dr. Kalyan was talking a little bit earlier. This is a proper curve for 5 VT, that how this soot and NOx formation varies with the equivalence ratio as well as temperature. So it mentions that you can clearly see this in this conventional combustion works in this zone, and if you are operating somewhere in this LTC zone, you can avoid that formation of NOx and smoke. And it shows that how we are exactly doing that. There is various strategies, various names you might have seen that. PCCI, RCCI, HCCI, there's a lot of acronyms for that. So, and along with that, there are certain challenges that used to come along with this all benefits. This is high pressurized rate combustion control, HC and CO, and narrow load range that we have. So every solution in engine industry used to tackle by two ways. One is this, we have the design development, and second is that using suitable fuel. I am focusing on fuel side. So this commercial fuels that we have is diesel and gasoline. These are suitable for their own applications. One is this diesel that is that's pretty well known. So for LTC, I am looking for optimal reactivity as well as better volatility that is going to properly focus towards LTC. So this tailoring of property that I am looking for, there is two ways. One is the additives. Second is this blending of fuels of different properties. So in this work, I am presenting this blending of this particular work, and the selection was made on two commercial fuels, gasoline and diesel, and two alternative fuels, that is butanol and ethanol. I will blend them on the basis of their evaporation characteristics. Wherever diesel comes, because it's low evaporating in nature, we will perform the 10 and 20% of volume in the addition, the blend formation, and in others we will use a 20, 50 and 80% of blend. And the base fuels are measured. This is the property characterization that I have done. And just for the namesake that if I am using this, let's say EG20, it means that gasoline is 20% and ethanol is 80%, just for the name. And this is the fuel property that I measured. This is macroscopic property, so it varies linearly. That is what forces us to go for the evaporation rate. We wanted to see how these are behaving, these blends are behaving in microscopic behavior, because evaporation is a diffusion phenomenon. So we selected this hanging droplet method for evaporation study, and we performed it at ambient conditions because we wanted to see a low temperature combustion site, and we performed at 50 FPS using photon Pascal. The idea is this: I'll hang a droplet in this one fiber. There will be one LED array, and from the image processing, I'll get the droplet diameter, which will later on give me the evaporation rate. These are the typical images that I have shown for butanol. So first thing, pretty interesting that when I did this experiment, I got that gasoline is a multi-component system. It is pretty clear that lower components, lower hydrocarbons will evaporate fast, and then later on some non-evaporating part will be there which are higher hydrocarbon. Similarly for butanol, which is a single component system, it will be a linear curve. But diesel, you can argument that why it is linear itself. Because the evaporation that you can see is only 10% or 8%. It is taking very high time, it's non-evaporating in nature. So the blends that I have performed it is pretty clear that when I'm adding this 10% and this is for the diesel and this is for the gasoline, and when I'm adding diesel in the gasoline, it is showing a linear variation along with that, and non-evaporating part is increasing. And the next is that butanol diesel blend, again 10 and 20%. It is also varying, but it's not linear. Non-evaporating part is increasing, but it's not linear in nature. Similarly, for butanol gasoline, you can see here the blend proportion is 20, 50, and 80. So 20% pretty closer to butanol, 50 is in mid, and 80% is again closer to the gasoline. Similarly, for ethanol, first I want to explain this how ethanol behaves. Ethanol first comes pretty quickly because it's a single component system. Again, it used to have a non-evaporating part. The reason was that ethanol is hydrophilic in nature. It used to absorb some amount of water and it will maintain its non-evaporating part. We have tested up to 600 seconds, 600 minutes. And then this, you can see this ethanol and gasoline. It's because both have a really high evaporating nature. You can see the clubs, it is clubbing in all the sense. And here similarly in this ethanol and butanol. But here you can see it's a linear in fashion. So the overall conclusion, and you'll get the understanding why I perform this work. First of all, pretty clear that addition of diesel is increasing the non-evaporating part, which is going to be there. That you can pretty clearly see from this results that from this butanol result, it is going to be there. And similarly, in this gasoline work, it is increasing this non-evaporating part. Second conclusion, that evaporation behavior of single component with single component is different, and multi-component and multi-component is different. This single component with single component and multi with multi, these are going to vary linearly. That is pretty clear from this. If we see single component with single component, that is ethanol and butanol, it is varying linearly. Similarly, in the case of gasoline and diesel, it is also varying linearly. But it is different for if I am using a multi-component with single component. It is not going to vary linearly. It is going to hold its property for a certain duration, up to a certain blend percentage. And third part was this blends used to accommodate this hydrophilic nature of the ethanol. That actually clearly we can see in the plot. This if I am using any blend. So this was a curve for the ethanol. If I am blending with the other fuel, it will help me to release those properties, that hydrophilic nature that ethanol contain. It will make it better. So that and lower, that is a pretty common, that lower density viscosity and surface tension is used to help in the evaporation. And it also depends on your fuel nature, that multi-component or single component. So this work with the help of Nikhil Surendran, he is from IC's lab, IT Madras. And NCCRD, I think most of you know that. It is a new development facility that we have in IT Madras. Thank you.
So, do we have any questions for the speaker?
Yes.
You have done the scanning at normal temperature.
Yes, sir.
How do you consider that evaporation is supposed to be out of that?
So diffusion phenomena, it's a molecular diffusion, that air particles will, because of the convection itself. Even you can say that in the diesel, why it is happening because of the molecular diffusion.
But evaporation starts at near about more than 100 to 200 degrees Celsius.
That is for the low evaporating systems. If you are talking about butanol and diesel, you just keep it in a bottle that you can feel that it will evaporate within a certain duration. And we are seeing this in a very high fashion because we are using a really small droplet. Evaporation rates will be higher at smaller if you are having a lower diameters. That is in 1 mm, range of 1 mm, these diameters that we have. Yeah.
Somewhere I heard that you used diesel gasoline blends.
Yep, diesel gasoline blends we have.
What was the ratio of these?
10 and 20. That is why we actually for diesels, that is what I mentioned. For diesels we are using lower blends because of the evaporating nature. So gasoline will be 90% as well as 80%.
Was diesel and gasoline 20% exactly miscible, or did you use some additives or something?
No, it's miscible.
20%.
Both are hydrocarbons and natures are same, so it's miscible.
28.
And for the miscibility, that we have done this we call it physical separation method that we have tested it. Yep. Any other question?
If not, you have a question? If not, then let's thank the speaker. Thank you. So, one speaker is missing, kinetic modeling of small instrument. Anyone representing from that? No? If not, then we call the end of this session. Thank you very much.
Okay. Now I request to Professor Frank Winter to facilitate our session chair.
Before we stop, we want to thank our session chair. Thank you very much. Yes. Thank you very much. Sure. Very much. Yes. Thank you. Enjoy this.
Okay, we can have some tea as snacks. We are a little early, so maybe we can see the posters and things.
Next session we have at 11